So the topic for this video is something I'm doing for a class, but I just thought it was kind of neat, so I thought I'd make a video of it and put it on the channel. It's a kind of probabilistic way of reconstructing data when you have missing confounders, but a way to get data on those confounders from a similar population. And it's kind of an advanced, uncommon epidemiology topic, but I think it's pretty cool, so I'm going to share it. Um, so just some background on the data that I'll be talking about. Um, the topic of my PhD is on infective endocarditis. So that's an infection of the inner lining of the heart, like here, kind of usually around the valves. And it's particularly associated with IV drug use. Typically, there's three types of treatments, so antibiotics, valve repair, and valve replacement. And as the severity of the infection increases, the type of treatment that's called for generally jumps from antibiotics for less severe infections up to valve replacement for the very severe types of infection. And that can depend on how much the infection has had time to grow. It could also be the type of bacteria, but yeah, this whole mechanism of how treatment is informed by severity breaks down for IV drug users because they're particularly frail during the surgery and after. So when they undergo surgery and they go back to using injection drugs, they're at a much higher risk of dying from complications and reinfection. So it's unclear whether, like, regardless of how severe the infection is, whether antibiotics might actually be the safer option, regardless of how severe. And that's the basis of what I'm trying to study. Um, so yeah, just to kind of set the stage, ICES is the main data repository at my university for health data. So a problem with ICES is it's typically data that's collected by hospitals or insurance agencies, so it might not have all of the information that is relevant to us because that might not necessarily be relevant to those who are generating this data. An example of this is so the main exposure here is treatment, the three I described before, and mortality over 4 years. And an example of a missing confounder that's pretty important is intracardial abscesses, where the more severe it is, the more likely you are to receive one of those more invasive treatments. And it is an abscess in the heart, so it obviously has an influence on mortality. So this is the structure of the data. So I don't know how many observations there is in the actual data set, but here I'm just saying it goes up to 3,000. And each individual has a treatment that they have been given and whether they died within 4 years of that treatment. And a major piece of information I'm missing is whether they had an abscess. But if I was to do a supplementary cohort with only 200 individuals where I collected the same information, the treatment they got, as well as their mortality after 4 years, but also their abscess status, this would enable me to, like, provided that this is a very comparable population to the one previously, what this would enable us to do is come up with the probability of having an abscess for each combination of treatment and outcome. So basically, we just take everyone who got antibiotics who died within 4 years and figure out the proportion of them that had an abscess, and we can do that for each combination. And then it lets us kind of reconstruct the ICES data that is missing this abscess data using probabilistic methods, so it's specifically Bernoulli trials. So yeah, this is the information we would need to do such a Bernoulli trial. We have this individual without their abscess information, but we have their treatment and outcome combination. And from here, we have the probability of an abscess for individuals in our supplementary cohort that had that treatment and outcome combination. And that lets us conduct a Bernoulli trial. And a Bernoulli trial is like a perfect example of a Bernoulli trial is just one coin flip. It's basically it's a trial in isolation where there is an event typically binary, that has a defined probability of happening. So when you flip a coin once, that's a Bernoulli trial. Let's say it came up heads, and you do it a bunch of times. You're running a Bernoulli trial every time you flip the coin. If you had like an unfair coin, some kind of trick coin where the probability of heads is lower, um, your collection of Bernoulli trials will start to be skewed towards tails. So just to kind of simulate how that would apply to what I'm doing, this first individual received antibiotics as their treatment, and their 4 year, or so yeah, they didn't die within the 4 years of follow-up. So for that pattern of treatment and outcome, the probability of having an abscess was zero point 0.1. So to represent that, I have 10 cards here, where abscess is written on one and no abscess on the rest. So there's a 1 in 10 chance of um, this card being drawn. So if you were to shuffle that deck and pull out a random card and it was no abscess, we'd be able to put that 0 in for abscess. And that's a simulation of how we can use like a probabilistic method to reconstruct this data set. And just another example is this individual had valve repair and they did die within 4 years. And for that individual with a probability of an abscess of zero point 0.4, that can be represented with 5 cards here, where 2 have abscess written and 3 have no abscess written. And yeah, and that's just because 2 divided by 5 is zero point 0.4, I think. Yeah, 2 divided by 5 is zero point 0.4. And so if we shuffle that, and draw a random card, and this time we drew abscess, so we would assign that individual an abscess as their score. And if we keep doing that, we're able to pretty much reconstruct the entire data set. Remember, this isn't real data. For this was a person, and we don't know what their abscess status was, but we can have an idea of what it was likely to be using those Bernoulli trials and the supplementary cohort. And analysis on this is obviously not as robust as if we had this data, but what it allows us to do is kind of do some uh, bias analysis, like sensitivity analysis, to see just what kind of influence having this abscess data might have had on our results. And yeah, it's a neat little method.